In this video, we will describe the various parts of a liquid-solid phase diagram, and we will do this looking at a relatively simple system and describe the parts. What we're plotting is the temperature versus, in this case, the mole fraction of silicon, so a binary system, magnesium and silicon. And so we see a number of regions, and so what I want to describe is what these regions correspond to. When we have lines, they're separating regions at different phase, and so we'll start looking at the liquid region. So what I've done is label the melting point for silicon and the melting point for magnesium. And we have liquid in this region, so the first thing to notice is that the temperature we have, solidification or melting, is a function of the composition. So unlike a pure material in which all the phase change occurs at one temperature, here it occurs at different temperatures for different compositions. So let's look at a situation, understand what would happen if we start in the liquid region here. We start along the temperature. So it's important, since this is an equilibrium diagram, it's important that we do this very slowly so that we can maintain equilibrium. It's different from a gas vapor in terms of how easy it is to maintain equilibrium when we have solids forming. So if we start here and we start cooling, we stay in liquid region until we hit this line. At this line we start solidifying. The first thing that forms is pure silicon. So at this temperature we're going to have liquid with this composition, about 70% silicon, and we're going to have pure silicon in equilibrium. As we continue to remove energy, cool it down, we're going to follow along the liquid because we're changing the composition of the liquid. We're removing silicon, so we're enriching it in magnesium. So at a later time and temperature, we still have equilibrium. We have now silicon, pure silicon in equilibrium with the liquid, and we'll keep doing that till we get to here. We'll talk about what happens there in a minute, which means this whole region is liquid and solid silicon in equilibrium. So this region here, cross-hatched, two-phase region. And the same behavior would happen if we started over here, except when we get to this point, the phase that is in equilibrium is this. Well, this corresponds to, which is actually a compound, two magnesiums for every silicon, and so we have again a two-phase region, and again cooling. Phases in equilibrium have to be at the same temperature. We get liquid that becomes enriched in magnesium, and we're removing silicon and magnesium from the liquid phase, and so this entire region now is a two-phase region that corresponds to liquid, and then Mg2Si solid. So I've indicated in green this two-phase region, and then you can see that likewise this is a two-phase region. This also in here would be liquid. Let me draw over to here. It's liquid plus again Mg2Si solid. So now we define three of the regions. Let's look at what happens in these other regions. If I indicate a point here in the solid region, what this corresponds to are two phases in equilibrium. This solid phase and this solid phase. So this corresponds to the compound, solid, plus silicon solid. So two distinct phases in equilibrium, and this entire region then are those two phases in equilibrium. This entire region then is magnesium solid plus Mg2Si solid. Again, two solid phases in equilibrium. So again, indicating in yellow, we have a region of two phases, and the amount of each is determined by the lever rule. So for example, let's say we were right here, 40% overall composition right here. What this corresponds to is a mixture of these two phases, pure silicon and this compound, but we're very close to this side, so it's mostly this compound. And we can use the lever rule to determine how much silicon and how much magnesium silicate. And we talk about lever rule in another video. So I've labeled on a clean diagram just to make sure all these regions are clear. Liquid, this region is two phases, liquid plus solid, two phases, two solid phases. Here, liquid plus solid, where the solid is a compound. Here, two solid phases in equilibrium. one of which is the compound. And if we're right on this line, then we have Mg2Si right along that line. So the one point we haven't talked about yet is this here, this point that's the eutectic point. And that corresponds to a lower temperature than, the lower melting temperature than at either a higher or lower concentration. It's a minimum in the melting temperature. And so we would start here and cool, we said we form solid silicon, and then we'd follow along equilibrium, right? Equilibrium has to be a horizontal line at the same temperature. We have silicon solid, right? This is silicon solid over here. And we have the liquid here with the composition changing as we remove silicon until we get to this point. So here as we're cooling and solidifying, the temperature is decreasing. When we get to this point, now the temperature no longer decreases, but we sit at this point and we now have solids forming that silicon and the compound. And we will sit at this point until all the liquid disappears and we have the appropriate composition that satisfy a mass balance. So this eutectic then is a constant melting temperature or a constant solidification temperature. If we were to start exactly at that composition and cool down, we would remain liquid until we get to here, and then both phases would form and all the freezing, solidification would occur at one temperature. And then as we cooled further, then we have two solid phases in equilibrium. And likewise, if we were to start over here and cool down, we would get the compound forming, and we move along this line where we're enriching in silicon in the liquid phase till we get again to the eutectic point, and now both silicon and the compound would form until we reach a composition, the combine of these two, such that we satisfy what the overall composition is of the original liquid. If we start over here, then we don't hit the eutectic point, but we move down along this line and we are forming the compound. So this is a description of a relatively simple diagram, because we can have multiple compounds in more complicated diagrams. We can have then multiple eutectic behaviors, and the ideas, however, are the same about whether we have one phase or two phases and what the compositions of those phases are.